So for our agenda today, we're going to be talking about two extensions that are going to help with our prototyping session here. The first being additive manufacturing extension, and the second one being Creo Simulation Live. We'll talk about some of the design challenges that these two extensions address, as well as some of their capabilities. We'll then do a Creo demonstration on AMX and CSL. And then I'll pass it over to Lauren to talk a little bit more about our additive manufacturing solutions. Okay, so next I want to quickly introduce EAC for those of you who may not know who we are. So EAC, Product Development Solutions, is made up of industry experts who are passionate about transforming the way that companies design, manufacture, connect to, and service their products. And we've been doing this since 1996. Our products, solutions, and services span the complete product development lifecycle, including computer-aided design, simulation, additive manufacturing, product lifecycle management, service lifecycle management, technical publications, IoT, and augmented reality. We are the leading premier PTC North America technology partner, offering the full PTC portfolio, as well as a leading global solution provider for over 20 years. We also partner with Formlabs desktop additive manufacturing solutions and Intamsys industrial 3D printers, and we'll talk a little bit more about that as we move forward with the webinar today. So we offer multiple services to help manufacturing companies achieve their business goals with a focus on process optimization and the digital thread. So this includes business assessments, training, data migrations, extensive technical support, engineering and design services, and much, much more. So we are actually headquartered in Minneapolis, Minnesota, but our employees are spread all across the US. We're within reach and ready to help no matter where your business is located. So that's a little bit about EAC, and now we'll get into some of the details about these extensions. So like we said in the agenda, we're going to start with the additive manufacturing extension. And first, I wanted to talk a little bit about some of the challenges that brought PTC to create this solution. So with additive manufacturing, or with the manufacturing process in general, oftentimes design decisions are driven by manufacturing constraints and limitations. And high cost and lengthy lead times are often needed to create these manufacturing tooling and manufacturing products. So because of this, designs are often over-engineered or rarely optimized due to the complexity of the manufacturing process. And that's why we have Creo AMX to help address some of those challenges. So AMX, the base package comes with a few different capabilities. And the first is, it has to do with the automatic creation of 2.5 and 3D lattice structures. So we can take these lattice structures and we can seamlessly analyze them and optimize them based on our design goals. And then along with that, we also have printer tray optimization, where we can set up our printer tray volume, place our parts in there, and there's some automated tools that help with that as well. We also have AMX Advanced package, so this would be the one step up from the base package. And this has to do mainly with metal 3D printing. So with the AMX Advanced package, we can connect to about 3/4 of all of the metal 3D printers that are on the market today. And we can actually use that 3D printer manager to conduct jobs right from the Creo interface. There's a few extra added configuration tools, automated tools that help configure your tray for 3D printing for metal 3D printing processes. And we also have automated support structures that we're able to create within the advanced package as well. All right, next we're going to talk a little bit about iterative design challenges and simulation. So up here on the screen, I kind of have a visual depiction of the product development process. So we usually start with a concept. We create a design, we iterate through that design. We then run our simulation, create prototypes, and manufacture our products. But oftentimes we see simulation kind of right in the middle here. After we've gone through and iterated to create a final design. But why is that? Why don't we use simulation more often and earlier in the design process? One of the reasons for this is because usually when we're dealing with FEA and simulation, we need to consult an expert, right? It's kind of hard to just pick up FEA solutions and just run with them without having that tribal knowledge of how to run them. Also, oftentimes we can't use the actual design model. We need a simplified copy, maybe a simplified representation, things like that. We need to defeature our part so that it will actually converge on a solution. And I think we can all agree that the product development process and design is a very iterative process. So if we're able to take that simulation chunk there and incorporate it within our concept and our design, and use it more early and more often in this design process, it'll save us a lot of time and money along the end of that design process. And that's where Creo Simulation Live helps us. So some of the benefits of Creo Simulation Live are first the speed. So Creo Simulation Live actually runs on the GPU of our computer, whereas standard simulation tools and actually Creo Parametric run on the CPU. And because of this, because it's using that GPU solver technology, we can very quickly and very interactively get that solution from our FEA results. And you'll see in the demonstration, it's for a simple structural analysis, it takes about 5 seconds to generate that result. Second is the ease of use. We don't need to be FEA experts to use Creo Simulation Live. Really, the purpose of this tool is to bring simulation to those people who are not experts, make it user-friendly, and things like that. It's also geometry enabled. So because we're running on that GPU and Creo is running on the CPU, we can make changes to our models. We can create and edit features. And as soon as we regenerate that model, we'll have a new result running in the background and be able to see exactly how those changes reflect our simulation results. And then finally, we have confidence that this is actually powered by ANSYS technology. And if you're familiar with ANSYS, they've been a global leader in the simulation space for the last 50 years. So some of the capabilities of Creo Simulation Live, we can run a few different studies. We can do structural, thermal, modal, and fluid analysis with CSL. Now, because it is running on our graphics card, we do have a requirement around that. So we recommend that you have a NVIDIA CUDA supported graphics card with a minimum memory of 4 gigabytes. So with that, I'll head over to Creo and we'll show you guys some of this technology. Okay, so for today's demonstration, we're going to be working with this part here, and it's actually an aircraft bracket. So as you can imagine with aircrafts, we have kind of low quantities, and we're going to want to incorporate 3D printing for actually some of our manufacturing products, right? Some of our final products are going to be optimized with 3D printing. So really what the goal of this demonstration is to take this part and simulate its use and application, and then optimize this part through the use of lattice structures and AMX. So the first thing we're going to do is run our initial simulation using CSL. So to get to CSL, I'll just head up to this live simulation tab. And as I open that up, you can see on our screen, we have our simulation study here at the top, as well as our model tree here at the bottom. So you can see I have a few different constraints and loads for this specific study, replicating the application. So we have this cylindrical surface on the inside of this as fixed, and then we have our 2 connection forces in their appropriate spots over here and here. All right, so once we have our constraints and loads set up for this part, we can go ahead and simulate that. All right, and you can see within about 5 seconds, we have our completed result. So we have that very fast, very interactive GPU check technology that is solving this FEA analysis for us. And we can see our result of about 410 megapascals. So what we're going to want to do is we're going to want to track these changes as we kind of iterate through this design. And we can do that by setting up a simulation probe. So I'm going to click on our simulation probe here. We'll choose max for the max von Mises stress for this entire part, and we'll go ahead and save that as a parameter. Now, along with this, we're going to want to accumulate our data through our different iterations. So I'll make sure I have this accumulate data checkbox clicked here. And now as we make these changes, what we'll see is kind of a bar graph view of our max von Mises stress through our different iterations. Now a little bit more on CSL. So right now we're looking at von Mises stress, and that's kind of the goal of this demonstration here. But we can also look at things like deformation. If we wanted to see how this thing is actually deforming, we get numbers for that. We can also animate that deformation if we'd like to see kind of an exaggerated view of that. And then within this legend, we can also look at a few different things. So local reaction force, resultants, normal and shear stresses in all of the directions, as well as principal stresses. But we'll keep this on von Mises stress for our goal here today. All right, so right now we have our initial simulation. What we're going to want to do is utilize the AMX functionality to create a lattice structure in this empty space in the middle of this part here, with the goal of reducing this von Mises stress. So I'll head over to our model tab, and to access our automatic lattice structure creation, it'll be under the engineering tab here. We'll go ahead and start that workflow for creating that. So the first thing I'm going to do is specify our lattice volume region. So I'm going to click on all of these surfaces inside of this region, and I'm just holding down Control to select all of these. So we have our volume region selected, and you can see our cell propagating over here. This would be an example of one of the cells that's going to make up the inside of this empty space. Now with AMX, we have a bunch of different lattice types that we can choose from, as well as different options within here. So for example, right now we have the beams lattice type selected. If we wanted to do a 2.5D lattice type, it would look something like this, right? Just kind of a rectangular lattice with a certain thickness. We also have formula-driven lattice types. So a lot of these formula-driven lattice types are used for things like fluid flow and heat transfer, which we aren't going to cover today, but it is useful to know. Now, once we select on what type of lattice type we would like, there's a few different options that we can set as well. So we can choose the cell direction, cell propagation. You can choose the cell shape, right? If I wanted to have a hexagonal shape to it, it would look something like this. If I wanted this type of cell shape, it would look something like this, triangular, so on and so forth. We're going to keep it at the box shape here, and we're going to reduce this cell size a little bit as well. So I'm going to cut this in half in all coordinate directions. So now you can see our cell updating as we make those changes. And I'm going to make a few more changes here. So we're going to reduce that ball diameter to 15 and reduce our cross-section size to 5. And then we also have this option for dangling beams. So if you can imagine, if this cell is propagated all the way through, and we can actually do a preview here to show you. You see how we have these dangling beams that aren't really doing anything for the structural integrity of our design here. We can change this option to remove these, just to save on material. So we'll go ahead and remove those. We're going to keep the density uniform for now, and we can go ahead and click OK to create that. Okay, so you can see as this model is regenerating, our Creo simulation live is constantly running that analysis for us. So in the background, it's always running that analysis. As soon as we make any changes, it'll go ahead and just kickstart that analysis again. So if we bring up our bar graph view of our different iterations here, you can see our first unchanged iteration had a max von Mises stress of about 410. And then our second iteration brought that all the way down to 104, right? So it's telling us we're moving in the right direction, right? We're doing the appropriate things to reduce the von Mises stress here. Now, what we're going to do now is we can actually utilize these simulation results to optimize this lattice structure. So we're kind of working with CSL and AMX in combination to create the final, most optimized version of this. So what I can do in CSL is I can go under the query and I can actually export these FEA results numerically. So for example, if I did a number of points to be probed, if I did 10,000, for example, it would take 10,000 different points along the volume of this part here, and it would calculate that von Mises stress. So if I do click accept here, it does take a couple minutes, so I already have done this previously. So now if we go back into our lattice structure definition, we can change the density of our lattice structure based on these simulation results. So if I change our variability to simulation, I can pull up those simulation results, and then I can specify my volume fraction. So I'm going to have a minimum volume fraction of 2, an average of 0.5, and a max of 0.8. And that's basically telling us that within this volume region, our average makeup of our lattice structure is going to be half of that volume. Okay. All right, so now that we have all that set up, I can go ahead and click OK. And you can see that new result here. And you can see some of these balls, some of these cross-sectional areas of our beam structure here are either larger or smaller to our initial result based on where those high areas of stress are, right? And again, if we pull up our bar graph view of these 3 different iterations here, we can see we went from 410 down to 104, down to 39 for our most optimized result. So it's really cool how these 2 extensions kind of talk to each other and how we can iterate through this design and make it as optimized as possible in a very quick and efficient way. So now that we have our final iteration of this example here, another thing we can do with AMX is we can prepare this for 3D printing. So if I go over to print, we see this option for prepare for 3D printing. And you can see it brings in this printer tray assembly for us. Now I can look at my printers list. And again, if we have AMX Advanced, it will connect to the Materialize or 3D Systems metal 3D printers. But if we're printing in plastic, like we are for this example, we can still add in our printer and bring in those tray dimensions to set up the configuration. So in here, if I click edit on this guy, you can see that the printer that we're going to be printing this out on is our CXC Formlabs printer. I have the model, we're using the Form 3 Plus and SLA technology, and then the appropriate tray dimensions in here as well. Now, in terms of arranging this part on our tray, there's a few different things we can do. Of course, we can edit the definition and just move it around like we would in assembly. But we have this automated tool here that automatically arranges this on our tray for us. So as we click that, you can see it brings in our model onto our tray. And we'll just want to double check if we have any areas of this part that are outside of that tray volume. You can see we might have a little space outside for this side of the tray. So we'll just go ahead and move that appropriately so that it's fully within that tray volume. Okay. Now with AMX Advanced, what we can also do is we can generate the automated support structures for this part if we're interested in doing that. We have plenty of options for editing those support parameters, as you can see as I drop down all of these different options here. We have a bunch of options for how we want to automatically generate those supports as well. If I did want to generate those supports, it does take a few minutes, so I've pulled it up in a different screen here. And it's this guy here. It would look something like this, right? Where we have our part, we have our automatically generated supports, and these supports are actually listed as a feature within our tray assembly here. Okay, so now that we have this part ready for printing, what we can do is we can export this as an STL file, because that's what the Form 3 prefers as a data file here. So I'll just save a copy, and we can choose STL. We can customize that export to choose options for our STL mesh and things like that. Now, if I went ahead and do that, we would get something that looks like this, right? STL file where we have all of our different facets, as you can see, so that our 3D printer can accurately print this. Okay, so just to kind of recap what we went through with that demonstration, we started with our aircraft bracket, and with the goal of reducing that von Mises stress, adding lattice structures. So we added that beams lattice structure. We then took those results from that simulation and optimized it even further, basically going from an initial stress of 410 megapascals all the way down to 39 megapascals. So with that, I'll now pass the presentation over to Lauren so that she can show the final 3D printed part, as well as talk a little bit more about our additive manufacturing solutions.
Perfect. Thank you, Stephen. So as this slide shows here, we offer a wide variety of additive manufacturing technology. FFF or FDM is actually one of the most common, and it's mainly used for jigs and fixtures or testing functional prototypes, and even end-use parts when we use more of those higher performance materials like PEEK and Ultem. SLA is more of the method that we use here to print a lot of our parts that need finer detail or really high resolution to capture that. And then SLS is more used for the really functional kind of small batch production parts. So I'm going to turn my camera on and bring you guys through our CXC here. Perfect. So welcome to our CXC. As you can see behind me here, we have our Formlabs 3D printers, the Form 3 here and the Form 3L. These use the SLA technology, which is using UV cured resin to create the part. And the Form 3 is great for sitting on a desktop. The Form 3L offers 5 times more build volume, so it's great for more of that bench top or working top station. And then we also have our post-processing units. The Form Wash is using isopropyl alcohol to kind of get any of that uncured resin off the part and rinse all the stickiness off the part. And after that, you put it in the Form Cure, which uses UV light and heat to bring the part to its fullest mechanical properties. So that's the Formlabs station there. We also have our Fuse 1 and our Sift. This is our SLS station, selective laser sintering. We use a powdered nylon to create more functional, stronger parts that are more end use and production ready. We also have a brand new partnership with Entamsys, where we offer the FDM solutions. And we're working on getting a demo unit in-house for that to be able to showcase that technology. So more to come on that. But yeah, as you can see with the SLA, SLS, and our FDM printers, depending on your application, we have a solution for you. And if you're local to the Minneapolis area and you want to come check it out in person, we'd love to have you. So we'll put our contact information up later so you can reach out and schedule a meeting. But now I want to show you guys the parts that Stephen created in his presentation earlier. We used the Form 3 to create these parts. They all took about 2 to 3 hours to make. And we used our standard matte gray resin, which is really great for just overall good strength. And the matte finish really captures some of that fine detail in the part. This first iteration here, which is the one that we did not have any of that lattice structure. So you can see there's a lot of stress there on the part. The second iteration here is where we added some of the beams and the lattice structure to the part. And the stress went from 405 megapascals down to, what was it, 104, Stephen? Yeah.
Yep.
So that you can see there. And then this third iteration, we added more of that variable density structure to the part. And I'm actually going to bring this around to show you and a little bit closer here. I left it on the build platform to show you guys how we laid out the part orientation for printing. And you can kind of see the support structures there underneath. And that reduced the stress down to 39. So ultimately giving us the best result in the end. So yeah, that's kind of all I had here, but let's turn it back to you guys.